In the previous video we found out that spherical surface is able to focus rays that is nearly parallel to our optical axis, or as we say, paraxial rays. It has ability to focus to paraxial rays, and we found out that formula is equal n divided by f prime is equal to n minus 1 multiplied by r over r, 1 over r. What does it mean? It means that our focal point depends only on index of refraction of medium and radius of the curvature. Also, it doesn't depend on h, this height h. So every ray that is nearly parallel, paraxial ray, to our optical axis will be focused in one point, and the distance of this point is equal to f1. We got this idea. Now let's look at the second case. What if our spherical surface isn't convex but concave? So in the second case, light or ray or light hits concave surface. Concave surface. Index of refraction of our surface is equal to n, and index of refraction of outer space is equal to 1. We have one parallel ray. Okay, it hits our surface at this point with some angle alpha. The center of this surface is somewhere here. Let's call this point is O, and it's center of our surface. Normal to the surface will be passed through the center of our sphere, and this normal will be here, somewhere here. Okay, this is our normal, and ray hits this surface at some angle alpha. Let's call this angle alpha. Okay, this is our alpha. This is direction of our ray. So because n, index of refraction, is n is bigger than 1, ray will continue here. It will pass, change its direction, and this angle will be beta. But if I continue this ray, it will be somewhere here. Yeah, it will be somewhere here. So if this angle is alpha, it means that this angle will be also alpha, because we have two parallel lines, and our normal to the surface is crossing these two lines. Okay, now let's call some angle beta. Okay, or let's call this angle is equal to beta, because this is angle of refraction. Okay, and this angle, for example, is gamma. Now let's draw a straight line from the incident point to our optical axis, and the height, the distance, will be h. And let's call this point S prime. This point is equal to just C, not S prime, but C prime and S. It means that this is our radius. This is our radius of our sphere. So as you see, this is our S prime. Okay, as you see here, this image looks exactly the same as this image, but it's just mirrored. Okay, if I copy this image, or duplicate and move near to my new image, it will be exactly the same. Let's just zoom in. As you see, they are the same. Okay, we have angle alpha, we have angle gamma. Okay, this angle is gamma. So it's just mirrored. It means that the formula will be the same. So you may ask how we can diverge our surfaces if light hits convex or concave. We don't know. Now let's agree on one condition. Okay, let's agree on one condition. We will assume that our radius is positive number when light hits convex surface. If light hits concave surface, our radius will be negative number. Then we can use this formula for both cases. I will duplicate this formula and write down it here, move it here. So formula this is the same, but radius will be negative number. Because our surface is concave. Now let's write it down. If light or ray hits convex surface, radius of the curvature will be positive number. Okay, R will be bigger than 0. If light or beam of light or ray hits concave surface, okay, our radius of the curvature R will be negative number or just less than 0. What will happen if I will put here negative number? My F prime will be negative. Okay, so because of that, in the first case F prime will be more than 0. In the second case, F prime will be less than 0. Okay, when light hits convex surface, F prime, it's here, F prime is bigger than 0, and radius of the curvature R is also bigger than 0.